The topic that we will discuss is relations. Topics are Cartesian products of two sets, ordered pairs, number of elements in a given Cartesian product, definition of relations, number of relations from set A to B if number of element in A is P and number of element in B is Q, then types of relations. Cartesian products of two sets and ordered pairs. Let A and B be two non-empty sets, then a set written in this form, A cross B equal to elements are of this type, A comma B, where A is from this set A and B is from this set B. So then this set is called Cartesian product of set A and B. For example, if I take A equal to 1 comma 2 and B if I take 0 comma 1, then Cartesian product of A and will be written as A cross B, where elements will be A comma B type, where A is from the first set A and B is from set B. And we can write these elements as 1 comma 0, 1 comma 1, then 2 comma 0, 2 comma 1. Here we see that altogether there are 4 elements, 1, 2, 3 and 4. Each element is called ordered pair. Each element is called ordered pair. Number of elements in a given Cartesian product and definition of relations. So here in above example, number of elements in set A was 3 and number of elements in set B was 3, and we saw that number of elements in the Cartesian product of A and B, it was 4. So that means number of elements in A cross B equal to 4. This 4 can be written as 2 cross 2, where 2 is the number of elements in set A and this 2 is number of elements in set B. Thus, if a set A has P elements and set B has Q elements, then total number of elements in A cross B will be P into Q. Now let us define relations. A relation R from set A to B is a subset of A cross B, and we write it as R equal to set of all ordered pairs, A comma B, where A belongs to A and B belongs to B. So if R is a relation from A to B, then R is nothing but a subset of A cross B, and that R will have elements as ordered pairs, where first component will be from set A and second component will be from set B. Let us try to understand by example. So here I have taken two sets A and B. A has 1 comma 2, B has only 1. Then Cartesian product of A and B will be 1 comma will have ordered pairs 1 comma 1, 2 comma 1. So from the definition we know that if R is a relation from A to B, then R is nothing but a subset of A cross B. So here let's find out the subsets of A cross B. Okay, and whatever subsets we get, each subset will be relation from set A to B. So here, as A cross B has only 2 elements, so number of subsets that it will have is 2 to the power 2, that would be 4. So it will have 4 subsets. So here I'm denoting each subset in this manner: S1, S2, S3, S4. So S1 will be itself A cross B, S2 will be null set, because null set is subset of every set, and S1 equal to A cross B because every set is subset of itself. And S3, here for S3 I've taken one element from here, and for S4 I've taken the another element. So we got S1, S2, S3, S4. These are the only subsets of A cross B. So as any relation from set A to B is a subset of A cross B, hence S1, S2, S3, S4 are relations from set A to B. Now, if number of elements in set A is P and number of elements in set B is Q, then number of all possible relations from set A to B will be equal to number of subsets of A cross B. So we know that if a set has m elements, then number of subsets that set will have will be equal to 2 to the power m. So here, as we know that every subset of A cross B will be relation from set A to B. That means if we find the number of subsets, then that would be equal to the number of relations from set A to B. So here, suppose A has P elements and B has Q elements, then total possible relations from set A to B will be 2 to the power P into Q. Like in this example, set A had 2 elements and set B had 1 element. That means P was 2 and Q was 1. So P into Q will be 2 into 1, that means 2. So total number of relations will be 2 to the power 2, that would be 4. So here we saw that total number of relations that we had from A to B was S1, S2, S3, S4. So only 4 relations we had. Now, example of a relation. Here I've taken two sets A and B. A contains 0, 1, 2 and B contains -1, 0 and 1. And here relation R is defined as this set of all ordered pairs where the first component is the square root of the second one. So here this A and B is given to us, and R is defined as this set of all ordered pairs where square root of A is the square root of first component is square root of the second one. So here we saw that 0 is square root of 0 and 1 is square root of 1. So we could have only 2 ordered pairs in this relation according to this condition. So here we got the relation. Now we'll write the domain of this relation. So domain of this relation will be all the first components of these ordered pairs, okay, without repetitions. So here 0 and 1, and range will be the collection of all second components of these ordered pairs. So again, range of this relation we got 0, 1. Now here we have two sets A and B. A has -1, 0, 1, 2. B has 2 and 3, and relation R from A to B is defined as set of all ordered pairs. Set of all ordered pairs for which first component is less than second component. So here we saw that A is given, B is given, so we would write down only those ordered pairs for which this condition is satisfied. So here we saw that -1, 2, 0, -1, 2, -1, 3, 0, 2, 0, 3, 1, 2, 1, 3, 2, 3. 2, 2 cannot be taken because this 2 is not less than this 2. In fact, they are equal. And here condition is the first component must be less than the second component. Now let's write down the domain of the relation. So domain of the relation will be the collection of all first components of these ordered pairs without repetition. So here -1, 0, 1 and 2 in the domain, and range will be collection of all second components from these ordered pairs. So here range, in range we have 2, 3, only 2 and 3. Now we have set A and B. A has 2, 4, 6 and B has 0, -3, and we have defined relation R from A to B as this, where the sum of first and second component is greater than 3. So we will write only those ordered pairs here which will satisfy this. So here 2, 0 we cannot have, 2, -3 we cannot have, 4, 0 yes we can have because 4 plus 0 is greater than 3. So 4, 0 we can have, 4, -3 not possible, 4 plus -3 will be 1, that is less than 3. 6, 0 yes, 6 plus 0 is greater than 3, so we can have 6, 0, 6, -3, that would be exactly 3. And here we need some should be greater than 3, so 6, -3 we cannot have over here. So we got the relation, and domain, in domain we'll have 4 and 6, and for the range we'll have only 0.